Welcome, everyone. My name is Jim Dowling, and Yogesh will join us shortly. And we're going to talk about how to build fraud prevention systems using machine learning. And in particular, we're going to talk about two platforms, Hopsworks, that I represent, and Inferyx, represented by Yogesh. Hopsworks is a company we built the first feature store for machine learning. So we build the first open source and first commercial feature store for machine learning. It's a platform that enables you to improve your productivity when you're building machine learning systems. You can collaborate together in different teams, your data science teams, your engineering teams. And as you can see, a quote from one of our customers, this is from American First Credit Union, and Richard wrote, they experienced a 3 to 4 time productivity gain when using our platform. All within 6 months, they got an ROI on our platform. So it's basically a platform that will help you get your data to your machine learning models and to build the pipelines to run those machine learning models. And we'll look at it in more detail later. Yogesh, do you want to introduce Inferyx?
Yeah, hi. Thank you, Jim. So hi, everyone. This is Yogesh. I'm the founder and CEO of Inferyx. Inferyx is a low-code application development accelerator, which helps you to build your applications with a no-code effort. And you can build any kind of, enterprise-grade AI/ML and a graph analytics applications. So there are different types of apps you can build using the Inferyx platform. Some of them are listed here, but they're pretty analytical in nature, where you can use the components of machine learning and graph. We are also the official partners with Neo4j, and you can use the platform accelerator to also build the graph applications.
Great, thanks, Yogesh. And I think fraud, many people who are interested in fraud have been using graph databases like Neo4j to build their features for the machine learning systems. And what we'll talk about today is a way to bring those features you've built in platforms such as Neo4j to production models, so to build production applications for fraud using that raw data. So the agenda for today is we're going to introduce the basic problem of fraud as a machine learning problem, why Hopsworks and Inferyx are suitable and best in class for building these ML-driven fraud prevention applications. We'll look a bit at how to build machine learning systems for fraud on Hopsworks and Inferyx. And then we're going to do a demo. We'll demonstrate some pipelines for fraud, credit card fraud transaction, and we'll also reference an anti-money laundering. So fraud in the general sense of financial crime, but we'll look at the specific problem of credit card fraud through pipelines in Hopsworks, and we'll look at how you can do low-code development of case-based management for these fraud systems with Inferyx. So I'm going to start with talking a bit about fraud. It's obviously a big financial problem. It costs a lot of dollars to many organizations globally, and it impacts everything from the reputation of the organization to the consumers, merchants, and investors involved in the financial transactions. And the existing systems we have for helping identify fraud, whether it's credit card fraud or anti-money laundering or many other types of fraud, they're legacy rule-based systems. So the idea is that you try and define a set of rules that encapsulate potential cases of fraud. And if those rules trigger, then you may not let the transaction pass, or you might just identify that this is a transaction suspected of fraud. But the result of rule-based systems is often that you're working on stale data. They don't run in real time. They work on, they can be brittle. Everyone, I think, is familiar with at least I am familiar with my bank calling me up when I'm in Paris saying, we're very glad to tell you that we found a fraudulent credit card transaction on your card in Paris. And I'm like, well, that's me. But what we'll see is that machine learning fraud prevention will give you a lot of benefits. So in particular, using Hopsworks and Inferyx, we'll enable you to work with fresh data, do continuous learning, and build an agile system. So machine learning is better matched as a technology for doing pattern detection for fraud. And we even have like a customer doing intrusion detection as a you can even see that as a very similar problem to fraud. You're doing pattern detection on real-time data as a way. It's a better, more powerful way of identifying fraud than existing rule-based approaches. And many organizations are aware of this. So if you take banks, for example, we can see that JP Morgan Chase are saying that AI is the way to look through these massive data sets. It is the technology to find these patterns, these fraudulent patterns, that the fraudsters are quite easily able to infer many of the rules that are encoded in existing systems. But with the graph-based features that we have nowadays, it's very hard for fraudsters to get around AI-based approaches. And Daniel Wu also mentioned from JP Morgan Chase is that the feature store is a key part of this platform, because that's the platform to manage our data for AI. We'll talk a little about that. Hopsworks was the first ever open source and enterprise feature store. And feature stores are a very useful way of helping the teams work together to build the machine learning systems, but also it's the key technology to get the data, the features that you create, to the online real-time models that you ultimately want to have to help identify fraud. So if you're a data scientist, you may be interested in framing fraud or financial fraud as a machine learning problem. So if you do that, what are the challenges of framing fraud as a machine learning problem? Well, the first one is that we're going to try and replace the rule-based system on the left. We can see we've got a rules-based fraud detection system. It says AML for anti-money laundering, but it could be credit card fraud transactions. And you can see we've got some simple rules, like if the number of transactions in the last hour exceeds a threshold 10, and that's just a configuration parameter, and the amount is greater than 50,000 euros, the bank is bad, then we'll alert that this is potentially a fraudulent transaction. And if the amount is greater than 50,000 euros and sent to a country that's considered bad, then alert. So these are the brittle rule-based approaches that are the dominant approaches right now. The machine learning approach, in contrast, will have two parts. You'll have one is where you train the machine learning model on some existing historical data that you've collected. You can see, if you're interested, we have more details in this blog link below, where we had a blog on NVIDIA with Swedbank about how they're using us to do this. But in the training part, you take your historical data about your financial transactions, and you have labels indicating if this particular transaction is fraud or if this one is not, and you can then train a model. So you take the data, you take that data and transform it into features, and you use those features and labels to train your model. We're going to fit the model. When the model is fitted and the model is now trained, we can use it on new data, so new transactions that arrive, to predict if they're going to be false or not, or fraudulent or not. So if this model.predict on the set of input features is true, then we can send an alert. And that's basically how machine learning based fraud systems work, is you train a model on some historical data, and in a training offline phase, and then in the online operational system, whether it's batch or real time, you call model.predict, use a model to make predictions. Okay, what other challenges do we have? Well, what we can see as well is that in nearly all fraud-based systems, we're going to have very large class imbalance between the number of transactions that are considered fraudulent and the ones that are considered clean. So as it's a pattern matching problem for machine learning problems that where we have these labels over the data, where we have a case and we say this was a dirty transaction, this was a clean transaction, we can use supervised machine learning, and we can also even use some anomaly detection unsupervised methods as well. But if we have this massive imbalance between the number of clean ones versus dirty ones, it becomes quite difficult to use classical supervised machine learning. Now, supervised machine learning can work if you can upsample the dirty transactions class and downsample the clean transactions. You may work for you. It may work that you need to do anomaly detection. We've done work on that as well. So there are many different techniques, and depending on your data set, there may be a different technique that will be best for predicting fraud in your particular financial area. Now, another challenge as a data scientist, if you're going to look at financial fraud as a binary classification problem, which is quite common, because if you're going to send an alert and say, I'm alerting that this transaction is potentially fraudulent, then you're not sending alert if you've decided the transaction is potentially not fraudulent. So really you're making one of two decisions. Do I predict that a transaction is fraudulent? So if we take the top left-hand corner here, we can see that we've predicted that the reality is we had a fraudulent transaction. We predicted it was fraud, so this is good. And then this is the green square. In the bottom right, we have true negative, which is we predicted a clean transaction or a non-fraud, and the model predicted not fraud. This is great. The problem we have is that if we do what's called a false positive, so we predict that a transaction is fraud, but in reality it's not, that's like me getting a call in Paris saying, hey, your credit card's being used falsely. It's inconvenient for me because I can't use my credit card at that point in time, and it will introduce some unnecessary work and cost. It's not the end of the world. The end of the world is if you have too many false negatives. If you miss all of the fraud and you predict that transactions are not fraud, in reality they are fraud, then you can be in trouble as an organization. You can end up with massive fines or even jail time by authorities and regulators. There's been cases recently in the Nordics of Danske Bank and Swedbank who were fined hundreds of millions and even billions of dollars. So the implication for data scientists is that this is what you would typically call a confusion matrix, and you can evaluate your models using what's called the F1 score on this confusion matrix. But here we don't consider all of the outcomes equal. They're not weighted equally. We care more about false negatives than we do about false positives. So we want to weight any model that we train to perform better on false negatives. That's really kind of one of the metrics we want to make sure that our model isn't bad on, because that can introduce massive cost. So I mentioned already supervised machine learning is very useful, but you can also go other way. You can use unsupervised anomaly-based approaches. So Swedbank investigated using generative adversarial networks as an approach, and they can see that we're getting great results. In China, 2 commercial banks reduced losses of about 10 million renminbi in 12 weeks by, again, using GAN-based approaches. So they used these generative adversarial networks to do telecom fraud detection. So they're very interesting. Just in general, we're still talking about the problem of fraud and machine learning. There are many different features that you can use to help predict fraud. I mentioned graph-based features. So platforms such as Neo4j are very good at computing graph-based features that can help predict whether transactions are fraudulent. So linking the origin account, destination account, transaction types to track the type of smurfing problems. And there's many features that can be computed on graphs that are very difficult for the fraudsters to avoid. Simpler features that are being commonly used are things like frequency. If, for example, we're talking about credit card fraud, how frequently a card is being used, the amount of money being spent on that card or transferred from a bank account. Time since features are important because maybe we have geographical attacks. If, for example, a credit card is used in one location, then after a short period of time, it's used in a different location, which is geographically too far away to be feasible. Then that can be a good signal of potential fraud. And then velocity changes. So if an account that's been barely used suddenly has a large amount of activity, that can be a good hint that there's something awry. You can find out more about the types of features that are used in 2 projects we have. We've actually got 3 projects that are great for getting started. One is on credit card fraud. There's a batch link here. There's also an online variant. So batch fraud systems are systems that will take your data maybe once a day and make predictions about those transactions, whereas online are doing it in real time. And then we have another anti-money laundering example that you can find more details of features. And there's good simulated data sets in these projects. So why are we talking here today? Why are Hopsworks and Inferyx talking about fraud and money laundering and financial fraud and crime for machine learning? Well, because Hopsworks as a platform, first and foremost, we support building these as batch machine learning systems, real-time machine learning systems, and we even support large language models, which will be very much used in the future to help us interpret a lot of these fraudulent operations. So to generate case reports and to give summaries of particular transactions that have been flagged as fraudulent. And also to explain why particular transactions have been flagged as fraudulent. So Hopsworks is an open platform. It's a feature store, a data platform for managing your data for AI, but it also supports processing of data, so feature engineering, model training, and batch inference either in Hopsworks or an external system. So you can use SQL, Pandas, Spark, and Flink all within Hopsworks or outside. And we have the industry's best LAs for real-time fraud. So if you intend doing real-time machine learning and doing real-time credit card fraud prediction, for example, you'll have an SLA. And we have the best SLAs in the industry, thanks in large part to the database that we built called RonDB, which is an in-memory distributed, highly available database. Also, Hopsworks is available on-premise. So compared to many well-known cloud platforms, if you're on-premise as a bank, you can use us. It's also available managed in the cloud. And I mentioned large language model support because Hopsworks provides support for compute as well as GPUs. You can even do fine-tuning on Hopsworks. You can store up to petabytes of data, and you can even do what's called retrieval augmented generation with Hopsworks, because Hopsworks has both a feature store and a vector database built in. So if you're building an enterprise system on top of fraud, Hopsworks is very useful because we meet all of the table stakes requirements for an enterprise fraud and financial crime solution. So apart from being efficient, we have security, role-based access control, single sign-on. We meet lots of regulatory compliance, not just GDPR and HIPAA, but SOC 2 and ISO 27001. We have extensive support for auditing and data governance. And of course, we're efficient and cost effective. Yogesh, do you want to say a couple of words about Inferyx?
Yeah, sure. So what we're looking at is the alert and the case management dashboard. So what Inferyx will allow you to do is configure your application in a low-code fashion where you can define your alerting rules, your case management rules, which will generate the cases for the investigators. Then the investigators can come and triage those alerts end to end. They can look at all the information about the case, the severity, and then there are various tabs here which I'm going to go through during the demo, which will show you what are the capabilities of case management. But you can perform your end-to-end triage within the case management itself.
Yeah, and Inferyx has a great low-code, no-code environment for building these end-to-end UIs for your applications.
Yeah, so some of the reasons like why would you want to use Inferyx, low-code, no-code, obviously that is the low-hanging fruit here. But apart from that, we have an interface which allows you to build your applications in a very point-and-click manner. We have different connectors which allows you to bring your data, build your features using the Hopsworks feature store. And then finally, it's a very scalable solution which allows multiple applications and users to operate in the same environment. So you can run pretty much all your various analytical or AI applications on a single platform. And then there are features around workflow engine where you can build any custom workflows as per your business needs. Again, I'll show you like how this can be configured through point and click and kind of be used and leveraged for the case management dashboards.
Great, thanks, Yogesh. So if you're looking at Hopsworks as a platform for building a financial fraud solution, you can see that there's many different layers of capabilities. I've mentioned quite a few already. At the bottom layer, we have a database called RonDB, which is highly available, low latency. We also have access to offline or large volumes of historical data for example, machine learning training models. So we efficient access through SQL API called Arrowflight and DuckDB. We have connectors to many different data vendors. So if you have got Snowflake or Databricks or Redshift or any SQL JDBC API, we can connect in without needing to copy the data over. Hopsworks has a built-in vector database, OpenSearch it's called. There's no graph database in Hopsworks, so it's where companies like Neo4j come in. And then Hopsworks has support for machine learning end-to-end. So we have a feature registry, a model registry, monitoring, model serving, data validation support with great expectations, model tuning. You can bring in any foundation models. And then there's support for doing development in the UI. And we'll look at some of these capabilities later. And I think where we differentiate ourselves from many platforms is very open to the compute frameworks you can run on top. So it's not just Spark, it's also Python, it's Flink, and it's SQL. Now, when you move up to a higher level, you say, okay, well, these are interesting capabilities. I can see I can build my machine learning system. But when you want to build machine learning driven applications that you might build on Inferyx, they'll be connected to Hopsworks at the level of the machine learning models and the data. So whether you're doing personalized recommendations or fraud prevention or anti-money laundering, credit risk, you're going to be connected into the data platform and the AI platform Hopsworks that can help also with identity resolution, which is a key building block for a lot of these services. So let's take a walk through what it means to work with a machine learning platform such as Hopsworks and find and discover your data for building your machine learning systems. So let's start with discovering our data. So if I have data in Hopsworks as a user, well, firstly, we can organize the platform and the data into what we call projects. So here we can see a user is searching for data related to loan approvals, and they can find some data, some features that can be used for training the models. They can search across descriptions, names, tags, individual features. And features can be shared across projects because a project is a kind of a security scope for your data. You might have a team that has access to all the features within a project, and a different line of business could have their own private projects. But you might have a group-wide project that everyone in the enterprise has access to. And Hopsworks is very flexible in allowing you to share those data between those different teams if necessary. So if you have the data, you might also like to have governance rules for your data. So maybe you want to define that a particular piece of data, a feature or a model is covered by GDPR. It's personally identifiable data. Maybe it needs a data retention time. Maybe the scope on which a particular asset can be used or a model can be trained with needs to be specified. So we have this great support for what we call schematized tags. So you as an architect can define them, and you can ensure that the developers attach these tags and they fill in. So you can see they're required to fill in particular values for it before they actually create the features that they're going to use and make available to others for training and using models with. Once you've discovered the data you're using, you may have discovered a model. You'd like to find its lineage. So this model, what data was it trained on? Where did that data come from? All of this is possible, again, in Hopsworks. So assuming we've now found our data and we've discovered what we think is good data sources to use for our platform, it may be the case that you need to use external data and write new feature pipelines that look at what the machine learning system you build will look like. And in fact, for all machine learning systems built on feature stores, we see the same pattern consistently. There's three main machine learning pipelines that you need to build. There's a feature pipeline, which takes your raw data and it transforms that data into features and labels. A training pipeline that will take your features and labels and output a trained model. And if you've got, if you're doing, for example, anomaly detection or LLMs, you may only have the input features and no labels, but that's fine. And then finally, the inference pipeline, which takes the trained model and the new input features. Maybe it's coming, daily by the feature pipeline, or maybe it's coming from the UI or app. That new data will be transformed into features or read up as pre-computed features. And with the model, predictions are output. And those outputted predictions are used by UI or apps such as Inferyx to build this AI-enabled application. So the question is, when you build these three different ML pipelines, the feature pipeline, train pipeline, inference pipeline, you need to pick technologies. So Hopsworks is very flexible. Often we'll see Python for all of three of these, but with large data, you might see Spark for the feature pipeline. And if you have real-time data, you could see Apache Flink, and SQL is also popular. Training and inference are typically in Python. And how these pipelines are connected together? Well, they're connected together with Hopsworks. So you write these three programs, you take your data, because in particular in fraud, you have to train on your own company's enterprise data. And that's your competitive advantage as well. So you're going to take your data, transform it into features, save those features in Hopsworks, and then train your models, save the model back to a model registry such as Hopsworks. You can use other ones if you want. And then your inference pipeline will make the predictions that will power your AI-enabled applications. You also need to have monitoring and logging, which is built-in support in Hopsworks, enabling you to make sure that the system is operating correctly. So let's walk through, that's how we build these systems in Hopsworks. Let's look at the specific example of fraud and what you would have as data to begin with. So here we can see a table of features. It's called a feature group in Hopsworks. And this has transactions. We'll assume they're financial transactions. We have a credit card number. a transaction date time event. So when did this transaction happen? Obviously, you'll probably have a timestamp rather than a date in the normal case. Here we have the city where the transaction happened, the category of item purchased, the amount of money spent, and then a label telling us whether this particular transaction was fraudulent or not. Now, there's some more detail on here that, the first two columns are not features. The columns in red are with these red values here are features. That's a feature vector. And then the label here, or the target we're trying to predict, is the last one, last column. And this is all great. This is the data we're going to use to train our models with, but also to make predictions with. But maybe we have features coming from other tables and we'd like to join them together. So in Hopsworks, we have an abstraction called a feature view, where you can, in very simple code in pandas, you can say, select these features from this table and these features from this table and join them together. And then with that view of features, that's the input features for your model, the schema, the input features, and the output, the target for your model. And then you can create consistent snapshots of training data and batch inference data, or even get rows of individual feature vectors for online applications with this feature view. So the feature view gives us consistent view of features for both training and inference. That's its job. Now, when we're doing our feature engineering, we've mentioned already we need to pick the best framework for the problem we're working with. If it's a batch feature engineering problem, we only want to generate the data on a schedule. If it's small data, pandas, larger data, but you still like to keep Python, you might use polars. If you have much larger data in the hundreds of gigabytes, Spark or SQL are the most common technologies. And if you need real-time data, Flink or Beam or Spark Streaming are typically the most popular frameworks. You can also, there is a Python-based framework called Bytewax. It's also possible to do real-time feature engineering with. Now, once you've developed your feature pipelines, particularly if they're batch feature pipelines, you'll need to schedule them to run or orchestrate them to run on a schedule. So if it's SQL, you can use dbt and SQL. Hopsworks supports that for many databases such as BigQuery. You may have a Spark application. Hopsworks, if it's run on Hopsworks, we have a built-in cron-based scheduler. There's also Airflow support in Hopsworks, but you can use your own external scheduler if you want, and Flink can run on Hopsworks directly. So these pipelines are the programs that feed the data to these feature groups or tables and update them all the time. So these tables are incremental tables. They're always growing. New data will be written on a schedule. And the reason why new data is always being written is because if your models are going to generate value, they need to keep making predictions on new data. So if it's a batch system, maybe the data will be updated daily and you'll make new predictions daily. If it's real time, these pipelines will be feeding data all the time in, and your models will be making predictions consistently in real time. Now, versioning in Hopsworks. So we do need some other attributes of Hopsworks or properties in order to make machine learning systems. We need to version our attributes. So Hopsworks, we version the features, the feature views as well, the models. If you want to upgrade a model from here, we've got fraud v1, we want to upgrade to v2, we may have changed the features used to train that model. So we need to also version our feature groups. And again, this is supported in Hopsworks. We're the only feature store that supports this currently. And it makes it easy to do things like rollback. If there's a problem in v2, you can just easily roll back, but you need to have the data that's connected to the models. So it's not just enough to upgrade the model version. That model version will be connected to the feature groups. For example, in credit card fraud, the feature groups might have information about how much money I spent in the last 15 minutes, how many credit card transactions I made. Maybe V2 includes more fine-grained. Maybe we've reduced it to 5-minute windows. And then we say, okay, V2 uses the 5-minute window, V1 didn't. So we need different models, and we need those to be connected to different feature group versions. When data is written to the tables, we should validate it, garbage in, garbage out. Hopsworks supports great expectations built in. So when you write data in Python or in Spark, we can define expectations over the data, and they'll be run, those expectations will be executed before the data is written to the feature store or the feature groups. And you can decide whether you'd like to alert on problems or whether you'd like to not ingest the data if it's problematic. It's very flexible. And then, of course, when you're in the user interface, we can then look at the history of these data validations as data is written to the platform. The other pillar of MLOps is Observability. So observability often encompasses both measurement or monitoring and logging. So Hopsworks has support for feature monitoring. So if your model, whether it's batch or online, is deployed, it'll be deployed against a training data set. So that training data set will have statistics computed over features. When we create a training data set, we'll compute the statistics. For example, here we have a reference window for a feature called has brand name, and we look at the mean value of it from the training data. And what we want to do then is observe from the new data coming in the detection window, has the new data shifted, or is there a statistically significant different distribution of that feature data with respect to the reference window? So what do we have? Data drift, as we might often call it. We can alert if there is, or you can eyeball the charts to see if your data coming in seems to follow the data distribution that you had during training. And then when you have deployed models, then these are a real-time model that you make requests to. So Inferyx, for example, if we connected to make requests on a model deployed on Hopsworks, you like to make sure that the performance of those meets your SLAs. So let's jump over to the demo, and I'm going to start by showing Hopsworks here. This is Hopsworks here. I mentioned we have projects in Hopsworks. So you can see I've got fraud here, but I have a lot of other projects. So this is my fraud project. You can see I've got some members in the project. If I go to project settings, I can add and remove people from the project, and I can give them data. You can give them a different role. So I can say for this gym person, you've data owner, data scientist. One is an owner in terms of GDPR. You're allowed to read and write all of the data, but data scientists can only train models and use features, not create them or update them. You can share then between projects. So let's look at how we do development in Hopsworks. So I actually run a fraud example that I had a link to in the slides. So I started by cloning this repository from Git. So we can do that in Hopsworks here, and it's called Hopsworks Tutorials. Sometimes you might need to install Python libraries. Each project in Hopsworks has, you can see, a Conda environment associated with it. So I can install libraries here. And those libraries will then always be available for development in Hopsworks. So for development in Python, we often use Jupyter. So I can open a Jupyter notebook from within Hopsworks. And this will run then code on the Conda environment that I've specified earlier. You can, of course, install libraries in here in Jupyter, but then they'll disappear the next time we start Jupyter, because this is a Docker image that we've compiled from that Conda environment. So this Docker image is running, it can run typically on a Kubernetes cluster. You can connect Hopsworks to Kubernetes, or we can run it for you if you don't have Kubernetes. So I cloned I'm inside Hopsworks tutorials, and you can see there's two fraud-based examples here. We've got fraud batch, and we can see in fraud batch we have three programs. We've got the feature pipeline, we have the training pipeline, and we have the inference pipeline. So let me open all three, and then we'll run through them. And we'll look at the output. So the first one, and this is a tutorial you can run yourself. You can go and use Hopsworks. There's a serverless version of Hopsworks that's actually free to try. You can create an account there and run this. You can run this code even from your laptop or even from Colab. So what's happening here is that we've defined actually some features. We have a package with some feature computations in here called transactions, fraud, and window aggregations. We're going to read some raw data from credit cards, about credit cards, some financial transactions, and then the profiles of the credit card users. And typically in a production pipeline, this data will keep coming on a schedule. So we might read it from a bucket in S3, or we might have it be pulling it from a database based on the last timestamp we use to read that data. In this case, I'm just reading it from file, but it's the same basic principle. So we're reading up the data as a pandas data frame. And then we're going to do feature engineering. Now, I won't go through all of the feature engineering here, but these are basically transformations on pandas data frames. We can use pandas UDFs or Python UDFs. Typically, pandas UDFs are more efficient. And what we end up with is the transaction data that the features that we're computing from the transaction data, like aggregates. So how often was here we can see the transaction volume and the moving average and the transaction frequency and the location delta moving average. So how much has between this transaction and previous transactions has the the location where the card's being used changed much. So when we've created these data frames, we log into Hopsworks here, and then we create this table of features from the, it's going to use the schema for the data frame. So this is when we're inserting the data frame into this feature group, it'll take the schema from there. We can specify it explicitly as well, but it's a bit more work. And we give each feature group a name and a version, and we say which column is the primary key, maybe one or more, and which column has the event time, because often we'll know the time of this particular transaction. So we do the same again for the aggregated window transactions that we compute. We insert them, and then we have our data in Hopsworks. So let's have a look at what that looks like. We end up with these tables here, the feature groups. You can see I have some feature groups were created. Let's have a look at one of them called transaction fraud FG. We can see these are very basic features, the age of the transaction, number of days until the card expires. So we would take the card expiry date and compute the number of days from now to that expiry date as well. You can get a quick preview of the data, so you can see it. It's not encoded, so it's human readable. You can do EDA here. We can see activity on this feature group, so how much data was ingested and all the operations on it. If we had data validation, then we can look to see if the data has been validated as well with our expectations, and we can see provenance as well. That's all available in here. Okay, so once we have our pipelines writing our data to the feature store, we can go and train a model. So training a model means selecting the features from these different tables and creating something called a feature view. So here again, we log into Hopsworks. Let's have a look at this, and then we get a reference to two feature groups, trans FG and window ags FG. These are two different feature groups containing aggregated features computed from our transactions. We select those features we're interested in from the two feature groups, trans FG and window ags FG, join them together. So they're joined on the, they'll be joined on the common join key, in this case, the credit card number. You can specify that explicitly if you need to. And then in Hopsworks, we can actually also declaratively define that some columns or features should be encoded. So we can say that, for example, any category columns, in this case, we have a category column, we want to label encode that. You can also, there's also support for min-max scaler for numerical features and standardization as well for numerical features. So what we did was we selected features, joined them together into this object called the query object. We said there was a column that's going to be label encoded. And then we create the feature view with that query object, which is our selection of features. We tell it which column is our label. We may have more than one as our label or target column. And then we say which of the particular columns we want to encode. And once we've done that and we have a feature view, we can use this feature view to create consistent snapshots of training data. So here we can say, create some training data that's split into training and test sets. Stored as a CSV file. You can specify a bucket in S3 if you want to store it there. 20% will be test data. So we're creating the training data, and then we can get our training data split into training and test sets and features and labels. We can train our model. In this case, we're training an XGBoost classifier model. And we can see then that we can look at the performance of it based on the predictions and then the actual outputs. Here's a very simple confusion matrix. And then we specify the schema to that model. We take the schema actually directly from the features in the training set and the labels in the training set. This could have been X test or Y test as well. It would be the same. And then we're going to save the model to Hopsworks. So the way we do that is, in this case, we're pickling the model that we trained, and we're saving it in a local file as a pickled Python object. So this is our model here, CLF, and we're using joblib to save it as a pickled Python object. We're also saving a confusion matrix there because we can store experiment results as well in our model registries to see how the model performed. And then finally, we're going to upload this local directory and save it as the model. And our model here is a Python model. And now the model's in Hopsworks. So let's have a quick look at that. We created this feature view here. This is the batch one. It takes some features from the different, you can see our label encoded column here. This is taking the categories coming from the features fraud batch FG and some other features coming from the other feature group. We can see down here that some training data set was created. And then the model that was created was stored into the model registry in Hopsworks here. And this is our model. We got an F1 score for it. There probably should be a confusion matrix, not that one there. So there's our confusion matrix. So we got our confusion matrix. We can have a look at that. And then finally, we're going to deploy this model in Hopsworks. So the deployed model will look as follows. And I'll show you the notebook in a second for it. And this deployed model can be called by Inferyx. So Inferyx can then use these models to build our online applications. So in this case, the model deployment is done. There's a couple of different notebooks here, but the model deployment was done in this online notebook, I think in here. So what we can do is we get a reference to our model registry, and then okay, it was in this one. Let's have a look. We'll go down here. So we've registered our model, and then we basically, in this case, we have to define a predict class. So we're going to implement the predict method and init methods. This will connect to the feature store and get a reference to our feature view. And when a prediction method arrives here, we'll go to the feature store to get our pre-computed features as a feature vector. And then we'll call predict on that feature vector. Here we're reshaping it to a NumPy array. This prediction script we're going to deploy as a model, a part of a model in Kserve and Hopsworks. And the way it works is that we will basically call deploy on that with our predictor script, the reference to this script that we defined earlier, the predictor class. And that's it. Then we can call model.deploy, or we can deploy it from the user interface. So that's basically it. So at this point now, we've taken our raw data, we've created features in Hopsworks. We have selected features to create a feature view, created training data from that, trained a model, and then deployed this model in Hopsworks. So at this point, this is the core of the machine learning system. And now we need to build an AI-enabled application on it with a user-facing interface. And I'll hand over to Yogesh for this.
Thank you, Jim. Let me share my screen here. So back to the Inferyx accelerator. So there are two components in Inferyx. One is where you can actually configure your alerting rule and case management rule and dashboards. So I'm just going to quickly show you that. And then you can have business user logging into the application to see the actual alerts and cases. So once you log into Inferyx, you can pick your application that you're interested in. Here I have a bunch of applications based on my access privileges. So I'm going into anti-money laundering. That's the one we are demoing today. So here what we can do is we can go through the data science package. So this is the low code module where you can configure your features, build the model into the training part. So once you train your model, the model will get stored into the Hopsworks repository. So what Jim was showing you was, a more Python-driven version. What I'm showing is a more of a no-code version, pointing to the Hopsworks repository. And once your model is configured, then you can configure your business rules, the alerts, and the case management. Okay, so I'm going to now flip into so this is more of a configuration idea. Once the configuration is done, then the business user can log in and they can see all the, the various alerts and the cases that are generated for that particular fraudulent transaction. So this is the interface for the business users. So again, you're going to see the same applications that were configured in the platform. So I'm going to choose the AML. And then once you get there, the business user will see the dashboard, a default dashboard. So you can configure your dashboards, any kind of visualization in a no-code fashion, and they will appear here as a default landing page for them. You have around 15 plus type of visualizations to configure within your application. Then you can look at all the alerts. So you can go to the alert can have its own dashboard, and you can look at all the alerts that are generated within as a part of the inference pipeline. And then you can also look at the cases, which is ultimately how you triage an alert. So I'm going to go into the case and I'm going to make a search here. I'll open a case from here. So this is a case management dashboard, which is basically, generated as a case in the system. So this is a case ID. You can see the severity, you can change the priority. So you can make some changes here. You can see the case is generated on a customer, and this is a customer ID. Now, if you would like to jump to that particular customer, you can just click here through the hyperlink and go to the customer details directly. Again, all of this is driven in a no-code fashion. So just through configuration, you are able to build this whole application in few weeks. Then I can look at the entity details. This particular case was pointing to a customer. So these are all the properties of the customer or the attributes of the customer that you can see. You can see what alerts are generated in the system and which has contributed to this particular case. It could be one or more. You can club multiple alerts into a single case. So for instance, if you have like, let's say 3 accounts and each of those accounts had an individual alert, you don't want to create 3 cases out of it. You can combine those alerts and create a single case out of it. And then from here, you can drill down into the alert itself. Okay, so I can make a drill down from here into the alerts. And then while that is coming, then you can also look at the link analysis. The link analysis is basically, it's connecting to the Neo4j graph database under the hood, and it's showing you all the nodes and the edges that are connected to this particular customer. So this is the customer we are talking. This customer is having this account. This is where he lives, and then this is the address, and then this is the bank where he is kind of transacting. So we can right click and we can, look at the details of this particular account, or we can just double click and you can try to kind of expand this whole thing and see how is it transacting with other accounts. So the intent of this case management dashboard is to look at why the alert was generated and, go through all the information, look at the surrounding network that is connected to this particular account to do further visual analysis. Similarly, we show you how the money is moving between different accounts. So this is like a flow of funds. So this is the account in question, and these are the accounts which are, transferring data or transferring money to this account. And then this particular account, which belongs to this customer, is transferring the money back into this more like a outbound area. So as an analyst, you can put your notes, you can attach documents. You can also configure a workflow engine if you like. So through drag and drop, you can build any business process workflow engine through this application. This is a very complex workflow engine which has been implemented for one of the customer, where you can initiate a case, you can decide how the case needs to be assigned, you can call an API, you can connect to a database, you can basically run any logic that you want through this particular workflow engine. And then this becomes the workflow of solving or triaging that particular case. Okay. And then every action that you're performing on this particular screen, that gets audited. So every click you make will be, so if anybody is looking at the case, that will get logged over here. If you're taking any actions on the workflow, even that will get recorded into it. Okay. And then you can also send notifications. So at various points, as you can see, when we are assigning a case, automatically we can send notifications. So you can send reminders where a particular case is created. And if the analyst is not taking an action, then you can send an automatic alert after every 24 hours. So, and those notifications will then get recorded over here once you send the notifications. Okay. So we have other menus too, where you can look at all the accounts, the customer. So all of these menus will appear dynamically based upon your business domain or use case. So if you're dealing with something which is, not banking and insurance, you will see entities which are related to the insurance, like claims, policies, and so on. But since you're looking at the banking use case, we're looking at accounts and customer. Okay. So yeah, this is what I wanted to present as a case management dashboard. Back to you, Jim.
Thanks, Yogesh. That was great. Okay, so that's it for mostly for today. I'll just bring us back to the slides. So if you want to learn more about fraud and machine learning on Hopsworks and Inferyx, you can reach out to us. And there's a contact detail for Nathan.Greenhill@Hopsworks.ai. You can join the Hopsworks Slack, and you can reach out to Yogesh directly. Thank you very much for attending this webinar, and hope to see you soon at the next one.